To get an understanding of Atwood's machine, we should be familiar with the tension of the suspended bodies. When a body of mass m is suspended by a thread, it is subjected to two forces: its weight acting downward and the tension acting upward. If the body is stationary, the weight of the body is equal to tension existing in the thread. When the body moves down, the effective force acting on the body equal to MA equal to mg minus T. A equal to mg minus T divided by m. This is our acceleration. We arrived this from this relation. Then the tension existing in the thread is given by the formula T equal to m into g minus A. When the body goes up, the effective force acting on the body is given by the formula Ma equal to T minus mg. From this acceleration A equal to T minus mg divided by m, then the tension experienced by the thread equal to m into g plus A. Now we may conclude that the tension in the thread increases when the body goes up compared to when it descends. But in the case of Atwood's machine, the tension on both sides of the thread remains equal. This equality arises from the fact that each side of the thread is connected to distinct masses. This is a Atwood's machine. A system with two masses connected by a string passing through a frictionless pulley is known as Atwood's machine. Here the masses M1 and M2 are suspended on a string passing through a frictionless pulley that is attached to the ceiling. Consider that mass M1 is at a distance x from the ceiling, while mass M2 is at a distance y from the ceiling. If you add these two values x and y, we can get a constant. X plus y equal to constant. We may express y in terms of x with the help of this equation, y equal to L minus x. If you differentiate this equation y equal to L minus x, we can get y dot equal to minus x dot, dy by dt equal to minus dx by dt. Since L is a constant, differentiation of L equal to 0. Since M1 is greater than M2, the respective force equations are: for M1, the equation is Ma equal to M1 minus T. For the mass M2, the equation is Ma equal to T minus M2. We have expressed y in terms of x so that the single coordinate x is sufficient to develop the Lagrangian equation of the system. Now the coordinate x is called generalized coordinate. This is the required Lagrangian equation. Now we have to find out the value of L. To evaluate the value of equation 1, we should know the Lagrangian value L equal to T minus C. T is the kinetic energy of the system and V the potential energy. The general formula for kinetic energy is T equal to half mv square. This is the kinetic energy corresponding to the first mass M1. This is the kinetic energy corresponding to the second mass M2. X dot is our velocity, so x dot square is velocity square. Here y dot is the velocity, y dot square is the velocity square. Already we have expressed y dot in terms of minus x dot. Therefore, we may get T equal to half m1 x dot square plus half m2 x dot square. If you simplify, we can get this relation. Kinetic energy T equal to half into m1 plus m2 x dot square. As you know that the potential energy of the system capital V equal to mgh. Here the mass m1 is at a distance x from the ceiling, whereas m2 is at a distance y from the ceiling. So that potential energy corresponding to m1 is m1gx. For the mass m2, the potential energy is m2gy. But here we have used a negative signs for both x and y, because the masses m1 and m2 are below the ceiling. Here already we have expressed y in terms of x, y equal to L minus x. So this x is present as such, but we have introduced a negative sign here. Y is replaced by L minus x. Here also we have introduced a negative sign, since the masses m1 and m2 are downward from the ceiling. Now L equal to t minus v is half into m1 plus m2 x dot square plus this term plus the second term. Then multiply this, you can get m2gl minus m2g into x. To find out the value of dou L by dou x dot, you have to differentiate the equation 2 with respect to x dot. Then the value is m1 plus m2 into x dot. d by dt of dou L by dou x dot is m1 plus m2 into x double dot. To get the value of dou L by dou x, you have to differentiate equation 2 with respect to x. Only these two terms are carrying x. Therefore, dou L by dou x equal to m1g minus m2g, which is equal to m1 minus m2 into g. On substituting the values d by dt of dou L by dou x dot and dou L by dou x in equation 1, you can get the Lagrangian equation of Atwood's machine. X double dot equal to m1 minus m2 divided by m1 plus m2 into g. Now we have to talk about the spiral cases. If m1 is far greater than m2, the value of x double dot equal to almost g is almost equal to g, because if m1 is far greater than m2, m1 minus m2 is m1, and then m1 plus m2 is also almost m1. So m1 get cancelled, then x double dot is almost equal to g. If m1 equal to m2, then the acceleration x double dot equal to 0. That's all about the Atwood's machine.